Looking at the sheer scale of this massive wave towering over the town and pine forest, the kinetic energy of a mega-tsunami is undeniable. The entire Pacific Ocean is ringed by deep subduction zones. These tectonic battlegrounds are constantly building pressure, capable of displacing massive columns of deep water in a matter of seconds. That precise sequence occurred on July 29, 2025. An 8.8 magnitude earthquake ruptured the seafloor off Russia's Kamchatka Peninsula, triggering immediate early warning systems. Looking at the leveled buildings and widespread debris here, it is clear why calculating the exact behavior of these waves is so critical. Forecasting the movement of a mega-tsunami is the single deciding factor between a successful coastal evacuation and total loss of life. This white and orange NOAA hardware is a dart buoy, humanity's primary line of defense and early warning for incoming tsunamis. The system works, but it suffers from a structural limitation. The seafloor sensors can only measure pressure changes at single, isolated points in the ocean. This 1D point data leaves massive spatial gaps, meaning researchers must extrapolate the behavior of a 1,000-mile wave train from a handful of fixed sensors. This diagram illustrates the assumption born from that limited view. Scientists assumed giant tsunamis were non-dispersive, expecting the energy to travel cleanly across the ocean as one single, stable wave. Building our defense networks entirely on single-point data left us with a severe blind spot regarding how extreme ocean events actually travel. Engineers built the Surface Water Ocean Topography satellite, or SWOT, to measure global water levels and monitor subtle changes in ocean circulation. But just 70 minutes after the Kamchatka earthquake struck, SWOT happened to pass exactly 600 kilometers from the epicenter. Instead of capturing isolated pressure readings from scattered buoys, SWOT captures high-resolution, two-dimensional swaths of the ocean surface. As this diagram shows, compared to a single blinking buoy, the satellite's sweeping radar covers an area a massive 120 kilometers wide. This chance orbital alignment provided a high-resolution view of the sea surface, exactly as a mega-tsunami crossed the Pacific. This top-down grid shows what the satellite recorded. Instead of a single wave, it spread in an intricate pattern. Tsunamis are highly dispersive. As the leading edge races forward, a train of smaller waves splits off and trails behind it. These scattered trailing waves carry immense energy, yet they were completely invisible to the isolated pressure sensors waiting on the seafloor. The old prediction models weren't mathematically broken. They simply lacked the two-dimensional mapping required to process the ocean's true physical complexity. Analyzing this 120-kilometer-wide swath of water showed that traditional models of tsunami energy were missing the dispersive behavior now visible on the 2D grid. By taking this turbulent wave data and reversing its complex movement, scientists realized they could forensically reverse engineer the entire natural disaster. The specific angles and spacing of those trailing dispersive waves are unique. They act like a physical fingerprint, holding embedded mathematical data about their exact origin. Researchers fed the two-dimensional satellite swath into their simulations to calculate the wave paths backward, tracing the scattered energy straight to its source. The calculations successfully pinpointed the exact location of tsunami genesis, the birthplace of the tsunami, down to a precise 10-kilometer radius. Upgrading from one-dimensional points to a continuous two-dimensional plane finally gave scientists the ability to mathematically rewind time and observe a tsunami's creation. The final step was combining the new 2D satellite imagery with the traditional dart buoy pressure readings to reassess the initial earthquake. This map visualization reveals the massive discrepancy they uncovered. The Kamchatka fault rupture expanded into a 400-kilometer tear, far larger than anyone originally believed. That makes the rupture a full 100 kilometers longer than traditional models had calculated using the buoy data alone. Moving forward, oceanographers must quantify this missing dispersive energy and permanently integrate two-dimensional satellite swaths into standard disaster monitoring. Transitioning to a two-dimensional view provides the missing mathematical variables needed to build warning systems that account for the ocean's actual behavior before it reaches the shore.